Hello, Chemistry 10HH students. This is Mrs. Altman. We are on video number 47, Liquids and Solids, Part 2. Here are our objectives for today's video. Pause here. So we talked about this a little bit last video, but we're going to go into a little bit more detail in this one so as to not make the last one too long. But when you have just London dispersion forces, when you have a larger molecule, meaning you've got a higher molar mass, more electrons, you're going to have more of an ability to form a partial charge. We call that a more polarizable electron cloud. And then you'll have higher London dispersion forces. And for very, very large molecules, those London dispersion forces can be more powerful even than dipole-dipole from smaller molecules. A really good example of this is diamond. Diamond only has London dispersion forces, yet it's almost impossible to melt diamond, or realistically impossible under most circumstances to do so because it has such strong forces. So if you have a high enough of a molar mass, it is possible to have London dispersion forces that are greater than the forces even from ionic bonding. Pause here. Right. So for the first one, I've got CH2Cl2, which has London dispersion forces and dipole-dipole, compared to CH4, which has just London dispersion forces. So even though LDFs can be greater than dipole-dipole, CH2Cl2 also has a higher molar mass, so that doesn't apply here. So CH2Cl2 will be the answer here. You could say because of the dipole-dipole forces, or you could say because it has higher London dispersion, higher London dispersion forces. For the second one, NaCl, that's ionic bonding. MgS is also ionic bonding, but MgS has a greater difference in charge. And then for the next one, Br2 just has London dispersion forces, and I2 also has just London dispersion forces. So I'm going to look at the molar mass. I2 has a greater molar mass, therefore it's going to have a greater London dispersion force. Pause here. I would include the picture here. We have just one more subtlety with London dispersion forces, and that's when we have branched versus linear hydrocarbons. So butane, that is an example of a linear hydrocarbon. It's in one line, whereas isobutane is branched. So these have very, very comparable molar masses. When you see situations like this, the linear hydrocarbons are going to be more polarizable, meaning they're going to have greater forces. So we apply it strictly to hydrocarbons. That being said, this could apply to things that are not strictly hydrocarbons. For example, ethanol versus, or not ethanol, isopropyl alcohol versus propanol. So if you have largely a hydrocarbon, you can see this. Usually you'll just see it in the context of hydrocarbons though. Pause here, you do not need to draw the picture. And then there's just one other type of interaction that you can see, which is an ion-induced dipole force. So when you have an ion, for example, NaCl, and then you place it near either something that has a temporary dipole or even a polar molecule, you can have an attractive force between the two of them. And that's why you'll sometimes see things that don't seem like they would dissolve in one another. We're not going to do a whole lot with this. I just wanted you to have seen it. Pause here. All right, so now that we're getting pretty close to being experts on comparing intermolecular forces, why does this matter? And the reason why this matters is because substances that have super high intermolecular forces will have high boiling points, they'll have high melting points, and then they'll have low vapor pressure. Vapor pressure is just the pressure on the surface of a liquid from the fact that there is always some things from the liquid state going into the gas phase. The reason why things with high intermolecular forces will have low vapor pressure is because they're not very able to go into the gas phase. Pause here. So we've got two substances here, and we want the one with higher vapor pressure. That means we want the one with lower intermolecular forces. In this case, we have butane and isobutane, so it's going to be the branched one. So in this case, it will be isobutane. I just wrote it out sort of fancy here, but isobutane will have the higher vapor pressure because as it is branched and less polarizable than butane, it also has lower LDFs. So that is all for tonight's video. Thank you so much for watching and have a great night.